Oh, students, the video cut out. So you missed me doing the problem. You missed some explanation. You missed me getting angry. But that happens. So we're going to continue and we're going to look at some different sorts of things. Basically, doing the various things you need to do to be able to solve problems with these currents and fields. All right, so let me erase. I cleaned the board, by the way. We're going to put in a current. So this is I. And we drawed in the field around it. And we talked about that. That was the right-hand rule. Right? We have our current here. And what we're going to do is grab and use that to tell the thumb is the direction of the current and your fingers are the direction of the field. So we kind of get the idea is that it comes out here and wraps around the board here. And then it goes into the board there, and it goes behind the wire there, behind the board. So that's the direction that we expect our field to go in. So if we put another wire in, right, then the way we solve the problem is we want to know what the field is here. So, and we do that with B is U naught I over 2 pi r. And you use the grab right-hand rule. Then we want to know what the force is on these things. Because what's going to happen is there's a magnetic field here and there's a current here. There's going to be a force on it. And then, so for the force, we use F is QV B sine of phi. In these cases, odds are sine of phi is going to be 1. We're going to put things at right angles because it's nice and easy. But sometimes we don't. And then this uses the pointing right-hand rule. And so if you remember that, your thumb is the direction of the current, and your fingers are the direction of the field. And based on this, based on finding the field from I1, it is into the board there. So we grab, and that puts our fingers into the board. And so from this, it tells us that our force travels to the left in this case. I'm hoping that's visible. That looks pretty visible. That's good. Now we're going to do the same thing. There's the right-hand rule that we drew here applies over here. So we can do the same sort of drawing. And so over here, the field is out of the board. This is B2. This is B1. And so when we do our right-hand rule here, I have to bend myself around. Thumb is the current. It goes up. I have a very crooked thumb, by the way. It kind of bends back. And then the fingers are out of the board as the field, and it pushes rightwards. And so the force here, and these are third law forces. Each wire puts a force on the other one, so they're on different free body diagrams. They are equal sized because we can take these things and solve for the force based just on the two wires. If we do that, I'll show you what that is in a second. And they're in opposite directions. And they're always in opposite directions. If we want to know the force just from the currents, it's just substituting in this magnetic field into this force equation. By the way, the force equation you want here is not this. its F is ILB sine phi. We focus so much on dealing with the force on a charge, and then when we switch to currents, it never quite gets there. We never quite get around to like, oh, we're doing currents now. We're just going to substitute in for B. And we're going to say sine phi is 1 here. So this is the force on 1. It's going to be mu naught I2 over 2 pi r. And then you just rearrange things. Mu naught I1 I2 L over 2 pi r. And this should be symmetric. So there is, all right, we'll have this distance is your L, it's the length of the wire that feels the force, and R is going to be the distance between the wires, because that's the radius is from the source of the field to the point you care about. Okay. So you could put some numbers in here, all right, and we'll do that. I should tell you what this mu naught is. It is a thing that makes the units come out correctly. All right, is coming from this equation up here. We need to go from current and distance to field. So mu naught is a number, and by convention it is exactly 4 pi times 10 to the minus 7 Tesla meter per amp. Right. And that's one thing, is that it sets the units appropriately. But the other thing is, this is a constant like epsilon naught, that the combination of them tells you how light propagates through materials. We'll get to that when we talk about light. But this is a material property. In this case, it's a material property of the universe. For normal materials, like the glass in the window that I have over here that you can't see, there is a mu, which is the permeability, and an epsilon, which is the permissivity. Right? And so that's where these come from, is they're saying, what are these numbers if we don't have anything at all? And they have values, and they govern the speed of light. So we can put in some numbers for this. All right, let's say R is 0.5 meters, and then we'll let I1 be 4 amps, and I2 be 3 amps. So let's find the force on I2. What we're going to do is find the field due to I2. That is, B is 4 pi times 10 to the minus 7 Tesla meter per amp times 3 amps over 2 pi times 0.5 meters. And so you'll get, this is going to end up being 2 times 10 to the minus 7 times 3 times 2. And so that'll be 1.2 times 10 to the minus 6 Tesla. And now we can do the force. We can go and write, well, what is the force on this thing? Well, the force is going to look like ILB sine phi. So it'll be, have I done that wrong? I have done that wrong. Someone should have said something. Me, I should have said something. There's a 4 here, because this is the field due to wire 1. So we'll have 2 times 4 is 8, times 2 is 16, 1.6. So this is going to be the current at I2 is 3 amps. The length here, we need a length, let's put in 1.5 meters. All right. That's the thing. If you have a longer thing, you'll have a longer wire, you'll have a bigger force, because you have essentially more charges interacting with the field. So ILB is going to be 1.6 times 10 to the minus 6 Tesla Now, you have to go to the base units for Tesla. So Newton per amp meter. So all of this will cancel out, and there's nothing underneath here. And sine phi is going to be 1. So 4.5 times 1.6. Is there an easier way to do that? 1.6 times 3 is 4.8. It's about 5. This is about 7.5 times 10 to the minus 6 Tesla. You can do that on your own. It's probably like 7.2 or something like that. Yeah, that's I think that is what it is. Yeah, it's going to be. Yeah. Anyway, now I'm sitting here thinking, is it actually that? Yes, it is. It is actually 7.2. And for the first time in the history of me teaching, I've done math in my head correctly. I'm almost certain of it. Now watch, someone will email me and say, no, that ain't right. So, remember where we started off with. This was two currents, one's going up, other's going up, and they attract. You could go and ask, what happens when I get a current that is moving downwards instead of upwards? So, erase a bunch of stuff we don't need right now. Just go ahead and erase that. Whoa, my marker's starting to slip. Yeah, it's starting to go. Let's say those are our two currents. One's up, one's down. So each one's going to have a field. This one, we get the idea of doing right-hand rule that on the left side it's out of the board, and on the right side it's into the board. But I2, we get the other outcome. We do our right-hand rule, and it says over here the field is into the board, and over here it's out of the board. So on these wires, there's B2 is into the board, and over here, B1. So this is at the wire. And then we do right-hand rule on these. So we do the pointy right-hand rule. So thumb goes up, fingers go in. The force is outwards. Here, we do like this, current down, fingers into the board, and the force is rightwards. And that gives us a rule of thumb. It says if our currents are in the same direction, it's attracting. If our currents are in opposite directions, they repel. I guess that's kind of a rule. Currents act kind of like charges for magnetic fields. They aren't, because there's some other stuff going on, but you know, this will do for us. I'm still recording. I'm paranoid because it cut off last time. So, you do want to be careful because you can have other situations. You can, for instance, erase this. You could have your current running at right angles. All right. So, we do the right-hand rule here. So I want to know what happens to I1 based on this I2. And so when we do right-hand rule on I2, this portion feels a force out of the board. This portion feels a force into the board. Because you would have to grab like this, so your fingers go in first, and then wrap around and come out. So the forces on this, we do right-hand rule again. We have here, it's current up, field into the board, and so your force is this way. Here, you have the opposite, because you have the opposite field. you have current towards the camera, current up, field towards the camera, you have the force this way. And so this is going to cause a torque. It's going to cause it to rotate. So isn't that fun? Don't rely on these in case you have something weird like this. Or if this is at an angle, you have to, whenever you see a problem, realize, what is it asking for? If it's asking for the field somewhere, don't worry about what the force is doing. If it just wants to know what the field is, calculate the field from each wire separately, and then you determine which direction they go, and then you add the vectors. These are all vectors. In this case, this wire provides a field out of the board. This wire provides a field into the board. And so you could assign some numbers and some distances and calculate what those would be. And I showed you an example of calculating the field. But then you look at these and you got to say, well, this is out and this is in. So in opposite directions, so I should be subtracting these. They should cancel out. And so that's, if you're calculating the field, that's what you worry about. These rules of thumb don't always apply as far as you'd like. So you want to be careful to go through the steps as rigorously as you can, as carefully as you can. So this is a fairly good stopping point, and we're going to come back and do a little bit more other stuff.